Hi there, my name is Thomas. I'm representing investmentexcel.com. In this session today, I will show you how to calculate and to visualize the empirical measure of the value at risk, VaR. And I will particularly show it on Apple Incorporated. I will focus on how to build the measure and how to invert the discrete distribution, which is the outcome of the building blocks in the calculation. On a general note, remember that VaR is most often used and indeed is most often the measure implemented because of regulatory requirements. The VaR is a parametric approach where the outcome of the portfolio in terms of dollars or in terms of percentage is described by a normal distribution where we assume on a forward basis, on a future basis, a mean and a standard deviation / variance. This approach has the big historical or empirical disadvantage that it doesn't capture, or the normal distribution doesn't capture, the often seen fat tails of the normal distribution or of the empirical distribution. So the empirical distribution tries to capture what's going on in the details of the distribution. And this is, of course, exactly what we want to look at with a shortfall risk measure like VaR. Alright, let's just take a look at a 10-year historical time series for Apple, which I have just simulated backwards in time with a geometric Brownian motion. And it's up here, the Brownian motion, the input we need to simulate, and we simulate backwards. It sounds a little bit contradictory, but that's what we normally do when we try to create data that doesn't really have to be aligned to real historical data, but are there merely to demonstrate some functionalities, which is the case here. Alright, the drift 8% per year, expected return, or some would say the required return on Apple, 8% normally. Volatility of the annualized returns, 15%. The model, the GBM, the geometric Brownian motion, start price 150, doesn't really matter here. Dollar doesn't really matter either. I have just written here the formulas that are behind the GBM. So here the stochastic differential equation, and here the solution to the stochastic differential equation. And we see the drift and the diffusion in here. And we also see that once we have generated the log returns inside the parenthesis here, total log returns, sum of the drift and the diffusion, we have to exponentialize. So this is what the GBM does on stocks. It creates log returns, and then afterwards we have to exponentialize to get simple returns. Okay, here I have split it in the drift, which is constant, the diffusion, which will change if I hit F9, because I have a randomizer inside here, because I invert the standard normal distribution to get a value of that distribution to multiply with the time scaled volatility. Okay, so now I have 120 observations, and although they are artificial, we just assume that these are actually the numbers for Apple the last 120 months. Now what we have to do in order to progress towards the empirical measure is to rank every single monthly return from lowest to highest. So this is what we do here. So 4% is the 49th highest percentages, and let's just see if we can find the lowest, which should be number 120. Okay, I should not have randomized again because I just found it before. Okay, here it is. Minus 36 is the lowest log return observed in the time series. I will not try to find number 1. It could be embarrassing if I can't find it. So, and here I transform the log return observed over here into real returns, not real in inflation terms, but simple returns. Simple returns on which we can calculate. And we have them down here. So there is no ranking yet. They have just been transformed. The ranking is done here. And I have ranked them reversely. So minus 30.2, and which corresponds to number 120, the lowest. And here you maybe say that it was minus 36 in log returns, but as we transform a negative figure on log returns, it gets actually lower. So when we have positive returns in log, like 4%, it gets higher, but when we have negative returns in log terms, it gets lower. Lower, like absolutely lower. So now they are here. So what we have to do now in order to create some sort of graphical visualization, we have to group them, which is what we always do when we make histograms, discrete histograms. We have to define some bits, as they are called in Excel, some groupings in which we make counts, how many are in this particular group on the x-axis of a histogram. And I have defined them here, the steps, so that I always get 25 groups in total. So you see it gets the lowest here, minus 13.2, this one, and it also gets the highest, 48.1, which is somewhere up or down here, where we have a rank 1. And now we let Excel count within each group how many observations do we have in each group. After that, we calculate the probability. We sum the counts, 3 divided by 120, and so on. And here the PDF, or should we call it discrete PDF? It's not really a PDF because it's not a density. It's a discrete observation, but I just tend to label it PDF because then people, they know what it is. So here we have the first histogram. We have segments on the x-axis, or bits on the x-axis, and we have probability upwards. And here's the cumulative discrete function, and it sums to 100. Then let's have a look. And we see it here. It looks like we have some normality, which is not that big of a surprise because I simulated the data from a normal distribution, so it's not that particularly, but it doesn't really matter here. We just have to show how it works. So this is the histogram, empirical histogram, and here is the empirical CDF histogram. and we see it moves gradually towards 1 or 100%. So now what we have to do is to calculate the VAR, and the VAR is exactly where the CDF is 5%, and luckily we have one on 5% here. So it's minus 23.9. So there is a 5% chance that the loss in the portfolio will be minus 23.9% or lower. And this is one of the things, so you always have to remember by the VAR measures in general. It's not an exact point. The 5% VAR 95 here, empirical VAR 95, it means that there is a 5% of obtaining this or lower. If we didn't have 5% here exactly, then I would have to make some kind of interpolation. So like here, the 5% is somewhere in between here. I would make some linear interpolation, and it will give me a result in between those two. Time is running a little bit out, so I will not show you how to make the linear interpolation, but it's quite trivial. But what I will do is just to show you another way of calculating the empirical VAR, and that's by fitting the CDF as an exponential function like I have done here. And we have a fit of 99.17, so rather good fit. And it seems like where the model doesn't work is up here. So no problem, because we are operating down here. And this function here is the CDF as a function of the VAR. So now I have to invert. So what I have to do is to set 5% in instead of y, and then calculate x. And you cannot do that in hand or with a simple equation. You have to use trial and error. So you have to build a formula in VBA or somewhere else where you guess on the x until you get 5%. But that's the way to calculate or to invert the empirical VAR measure, either from the CDF here, where you invert, which means that you look at the 5% and then you go down on the x-axis and find the corresponding loss, or you find the loss at 5% in CDF on a curve like this. Alright, that was empirical value at risk. Thank you.